Institute of Engineering and Technology.
Good morning, students. Today, in this video, I am going to cover the second part of new chapter, which is Fourier integral. Today, I am going to cover a special case of Fourier integral known as Fourier cosine integral. We have seen in case of Fourier series that if interval is symmetric, we can use the nature of function. And if function is even or odd, then it will reduce your calculation work and it will reduce the Fourier series as well. So let us observe whether we can do the same process in case of Fourier integral or not. Means, can we find Fourier cosine integral or not? And for that, we'll do some practice for same in this video. So let us start with the Fourier cosine integral of any function which is given by this thing, 0 to infinity a omega cos omega x d omega. We know that if our function is even, then it can be represented by same even function, equivalent even function. Equivalent even function simply means that it can be represented by cos function. So remember, the even function can be represented by another even function, and in general we are considering simple even function cos. So let us assume that our function is even function over the interval minus infinity to infinity. Then we know how to convert the even function in case of Fourier series. Today we will see how to use the same technique in case of Fourier integral. So over here, value of a omega is 2 by pi 0 to infinity f of x cos omega x dx. You can see clearly in case of Fourier integral, general case, it was 1 over pi minus infinity to infinity f of x cos omega x dx. It was 0 to infinity, but here we considered 2 upon pi by assuming that this function is even by nature. Let us see an example. Find the Fourier integral representation of this function and hence calculate these two particular integrals, 0 to infinity sine omega cos omega x upon omega, 0 to infinity sine omega upon omega d omega. Let us see how to figure out the solution. So the function over here is f of x, 1 for mod x less than 1 and 0 for mod x greater than 1. First of all, we need to understand this inequality, and for that, note that if mod x is less than a, that means it is inside the interval which is open interval minus a to a. If mod x is greater than a, that means it represents the answer or the value outside the open interval minus a to a. Now, the Fourier integral of the function is given by this general Fourier series. Let us consider value of a omega. Let us consider value of a omega. So it is 1 upon pi minus infinity to infinity f of x cos omega x dx. Now, we know that our given function is divided into three parts, minus infinity to minus 1, minus 1 to 1 and 1 to infinity. From minus infinity to minus 1 it is 0, from minus 1 to 1 it is 1 and from 1 to infinity it is 0 again. So if I consider my range minus infinity to infinity into three parts, minus infinity to minus 1, minus 1 and 1 to infinity, accordingly function will assume value 0, 1 and 0. So after taking this input, the only part which remains is 1 upon pi minus 1 to the cos omega x dx. Now we know that cos function is even by nature. And if you are integrating any even function over symmetric interval, you can consider the half range from 0 to any one side and you can double your answer. So it is 2 by pi 0 to 1 cos omega x dx. Now if we take integration of cos omega x, it is sin omega x, then coefficient is omega which will come in denominator. Taking the limits 0 to 1 will reduce this value to 2 pi sin omega x upon omega and sin omega upon omega minus sin 0 upon omega. Sin 0 is 0, so my final answer is 2 by pi sin omega by omega. And therefore, the value of a omega is 2 by pi sin omega by omega. Now similarly, let us consider b omega. Value of b omega is 1 by pi minus infinity to infinity f of x sin omega x dx. Taking again split of this minus infinity to infinity into three parts. Minus infinity to minus 1, minus 1 to 1 and 1 to infinity. Dividing this integration range into three parts along with values of f of x as 0, 1 and 0 will result in the next step into 1 over pi minus 1 sin omega x dx. Now, as sin omega x is odd function and interval or the range of integration is symmetric, it will give you answer 0. Now, taking both of these values a omega and b omega into the general Fourier series will give you f of x as 0 to infinity 2 by pi sin omega by omega cos omega x d omega. Now, this simply means that if I take f of x as the function, it will result into this answer. I am taking 2 by pi outside. Now, in my next step, I am taking this 2 by pi on the other side of the equation. It will give me pi by 2 times f of x. Now here, you can see clearly that pi by 2 is multiplied to 1, pi by 2 is multiplied to 0. And that means, if we have this function as a Fourier integral, we can figure out the value of this integration with help of this pi by 2 in this range and 0 in this range. But still, there is a point which is missing, and that point will be x equals to 1 and minus 1, because these are the points of discontinuity. If you want to find the value at those points, you should take average of this 2 at that point. Now, we are looking for a particular value where we can check 0 to infinity sin omega cos omega x upon omega d omega as 0 to infinity sin omega by omega. Now, the question is how to convert this integration into 0 to infinity sin omega by omega, and that we can achieve by taking different values of x. Omega is a fixed quantity which we cannot change. The only variable which is in our control is variable x. So what I'll do, I'll try to check for which x this quantity cos omega x will reduce into 1, and that is x equals to 0. So if I take x equals to 0, this integration will be sin omega by omega dx equal to, and as x equal to 0 is in this upper range, my answer will be pi by 2. So you can see that we figured out integration of 0 to infinity sine omega by omega d omega as pi by 2. If you try to solve this integration 0 to infinity sine x by x dx using any of your regular traditional methods, you won't be able to find the answer. This is the reason why Fourier integral is very useful. So I hope this technique of Fourier integral will help you figure out some very difficult integrations, and particularly in this case I considered Fourier cosine integral, where we are finding answer of a function which is behaving as an even function. As we have seen over here, the function was 0 outside the range minus 1 and it was 1. So it can be seen clearly that the given function was symmetric about y-axis. Now I will give you one small exercise. Instead of applying the formula for the general Fourier series, you try to see that the given function is even, prove that the given function is even by nature with help of using the algebraic test f of x, f of minus x is equals to f of x for all x given range. Then try to apply the direct formula for the Fourier cosine integral and check whether there is any difference in between these two answers. Whereas the general Fourier case is always applicable and it will give you answer always. But if you know how to use the Fourier cosine integral, it can reduce your work. Thank you.
LJ Institute of Engineering and Technology.